dot product with I, you got J, okay? So that the denominator become J cross product with K, you get I. I cross product with J, you get K. So I dot I plus K dot K. Then you get 1 plus 1, so you get 2 over 8. A power of 3 equal to A power of 3 over 4. So the denominator equal to A power of 3 over 4. Easy, right? Then now you have to find the nominator. Okay? So we have A3 cross product with A2 cross product with A3. We got A3 cross product with A1. A3 cross product with, I think this one is typo error. We have A2 cross product with A3, A3 cross product with A1, and A1 cross product with A2. I think A1 and A2, if not mistaken. Okay, typo error. So same thing lah, you just solve this one lah. You just substitute A2 and A3. Substitute A3 and A1, substitute A1 and A2, substitute it, then solve it, you'll get this one, and this one. Okay, so the reciprocal lattice for the face center cubic is equal to this one, and this one. So the reciprocal base vector is 3. At the same time, this vector is corresponding to the primitive vector of the body center cubic lattice in the reciprocal lattice. If you don't believe, you go back to the first chapter and you search for the primitive vector for the BCC. Okay, for the BCC, body center cubic, it's exactly same with these 3. Therefore, this table tells that if the shape of the crystal lattice, the real lattice is face center cubic, when you convert it to the reciprocal lattice, it becomes body center cubic. Okay, so the real lattice is the real lattice is face center cubic. After you convert it through these 3 equations, and then go through some simple vector calculation, then you will get these 3. And these 3 basically are the body center cubic primitive vector. Okay, so likewise, if these are the real primitive lattice vector for body center cubic, you go through these 3 equation, then you will get the reciprocal of the BCC as these 3. Okay, I want you to try on it. Okay, because in the exam, sometimes I will ask you to convert the BCC to FCC or I ask you to get the reciprocal lattice for the BCC, or ask you to get the reciprocal lattice for the BCC or FCC or HCP. Okay, so if your real lattice is body center cubic, then after you convert it using the equation, you will get the face center cubic. If you don't believe, try on it. Okay, work out on it. Then next, okay. This is a body center cubic, and this is a face center cubic. So this is the first Brillouin zone of the face center cubic, right? Face center cubic, the first Brillouin zone. So I magnify it. So we have special symbol. This symbol represents the center of the zone. Okay. Then this S represents the zone boundary along one of the axes. Okay. So that means that this here to here is S. Okay, I use different color. From here to here is S. From here to here is also S. From here to here is also S. As long as it is the joint boundary along one of the axes, x-axis, y-axis, z-axis, we all use the symbol x. Okay, for L, is from the origin to the diagonal. This is L. Here also L. Here also L. Here also L. Okay. From the joint boundary in the middle of the edge. So from this point to here. From this point to this point. K. From this point to this point. K. From this point to this point. K or K. Okay, so what is the application of this Brillouin zone? This Brillouin zone is very important in the band structure. Let's say for the band structure of silicon, this is how we represent it. Okay, you have seen something like this, right? Valence band, conduction band, and then this band gap. Remember that? Have you seen something like this? So in the real case, it looks like this. This is a valence band, and this is the conduction band. Okay, and there are many conduction band. There are many valence band. Okay, so the top of the valence band, I think this point, if not mistaken, I think this point, and the bottom of the conduction band, this point. So this is the EG band gap. So for the silicon, it only have a very small band gap, and the band gap is indirect. And this band structure is actually drawn on the reciprocal lattice. You can see that all these symbols are the Brillouin zone. Okay, Brillouin zone. Of course, later on, we also try to derive some simple band structure for some simple material. But at this moment, I just want to tell you that the Brillouin zone is useful in showing the band structure, and the reciprocal lattice also is useful in showing the band structure. Because for the band structure, we don't use the real lattice, but we use the reciprocal lattice. Okay, so this is the tutorial. I want you to try on it. The primitive vector of the hexagonal space lattice are given as A equal to this one, the real lattice A, real lattice B equal to this one, and the real lattice C equal to this one. Now I want you to show that the volume A cross B dot A dot B cross C, A dot B cross C equal to this one. Okay. Next, I want you to find the reciprocal lattice of A, reciprocal lattice of B, and reciprocal lattice of C. Okay. Then next, I want you to discuss and get the first Brillouin zone. But because it's in 3D, although it's in 3D, but it's not that difficult to skate it lah. But if you can, then you do it. If don't, then it's okay. Okay, doesn't matter. So what I want you to do is just for question 1 and question 2. Okay. Question 1, I want you to get the volume A dot B cross product with C. And then secondly, I want you to get the reciprocal lattice of A, B, and C. Okay, that's all for this chapter. And then I will proceed with chapter 8.